Section 3.2 is titled Addition and Subtraction of Whole Numbers. So before we get started, let's as a real quick reminder, what are whole numbers? 0, 1, 2, 3, and so forth. So no fractions, no decimals, no negatives, and it does include 0. That's important to know. All right, so the first thing we're going to talk about is what addition of whole numbers means. So if you have A and B and they're disjoint finite sets. Oh dear, did we see the word sets? Yes, we did. Disjoint finite sets. So think Venn diagram, circles that do not cross. Or if they cross, you got a 0, big whopping 0 in the middle kind of thing, okay? Non-overlapping sets. If you have the number of elements of capital A set capital A equals lowercase a, and the number of sets in set B equals lowercase b, then A plus B is the number of elements in A union B. The numbers A and B are called the addends, and A plus B is called the sum. All right? So when we found the cardinal number of unions before, we had this sort of weird issue that if they overlapped, which they most always did in the ones we were doing, we had to take the number over here, and subtract where they overlapped. You guys know what I'm talking about? Was that overlapping business going on? Well, these don't overlap, so I don't have to do any of that. So let's do an example. This says to give an example of why the definition of addition A and B must be disjoint. So an example means let's create actual sets A and B, and they're not disjoint. They have something in their overlap, okay? So I'm going to do it with a list of numbers, or you could do it with a Venn diagram would be fine. I have a list of numbers in my mind. So I'm going to do 1, 2, 3, and 4. And we'll let set B, it has to include something that's here, so let's include a couple of things, 3 and 4 say, and then maybe we have also 5, 6, and 7. All right, so what is the cardinal number of set A? 4. There are 4 items in set A. What is the cardinal number of set B? It's 5. And if I take this and I find the sum of the number of elements in A plus the number of elements in B, what do I get? 9. Okay, everybody good so far? Now let's come back over here and let's find A union B. What would A union B equal? 1, 2, 3, 4, 5, 6, 7. What are the number of elements in A union B? 7. And the whole point of this exercise was to show that when they overlap, these numbers don't match. Right? These are not equal. So in order to make this work, we would have had to have them be non-overlapping, non-intersecting, disjoint sets. All right. We're going to do different operations through the next couple of class periods, maybe 3 class periods, for addition, subtraction, multiplication, and division. We're going to have 4 operations, our 4 basic operations, and there are different models for understanding what those operations look like in terms of real-life application kind of problems. So we're starting with addition today. The first model for addition is called the set model. It's typically used for whole objects. Okay, so I know we're using whole numbers, but it's objects that can't be divided and make any sense. You know, like people. We don't divide the people in half. It doesn't work. All right? But the problem is, like, there are some things that we could divide in half and it would make sense, like cookies. You guys with me? Miles. Okay, so this one is the one that's whole objects. So here's your example. Liz has 3 blue crayons and 2 red crayons. If she combines all the crayons, how many crayons does she have? Okay. When we talk about a crayon, even if the crayon's little bitty, we don't talk about it like a half a crayon, do we? We really don't use language like that when we talk about crayons. So it fits inside of this description very nicely. And I'm going to show you, as we work through these, concrete visuals of what you could do when you're working very young children on how this works. So this says that we have 3 blue crayons. So here's 1, 2, 3 blue crayons, right? And then it says I have how many red crayons? 2. 2 red crayons. And the total number of objects then here is 5 crayons. If you don't have colored something with you, that's fine. You don't have to color these. You could just write the word red inside of them. Like, that's what I did on my paper because I didn't have any colors when I actually created my notes. Okay? But if you have colors, that's fabulous. So this is the set model. The other model is the number line or measurement model. So this one is typically used for objects that can be partitioned. Right? This is the cookie example. This is the, what else is a miles example, if you were talking about running miles or something like that, or driving miles. Typically used for these kinds of things. Joe has, for example, 4 feet of wood and 3 feet of aluminum. How many feet of building material does Joe have? So the imagery for this very much feels like you're kind of putting the objects end to end almost, right? That's why you're hearing this sort of number line imagery used. So if we started with 0 and he had, what was the first one? 4 feet. 1, 2, 3, 4. You can almost see, here's my piece, was it wood first? Here's my piece of wood, and it's on the number line, and it extends from 0 out to 4. And then he has aluminum that's 3 more. So here's 1, 2, 3, more than where I was. And we have aluminum right over here. And 3 more than 4 would then be leaving me at 7, so we have 7 feet of building material. This picture looks quite different than the last picture. It really does. This picture wouldn't make sense for my crayons. Not really, because especially when we talk about the fact that the crayons, unless they were brand new, are probably all slightly different in length, right? Doesn't really make sense to do the crayons like this. And this picture also, like if I tried to do the aluminum wood picture in the other example spot, it doesn't make sense to draw them separately. The piece of wood's 4 feet long. It's not 4 1-foot-long pieces of wood, right? So the images are actually a little bit different when we start to think about them, and they mean something quite different. All right, another definition for you, less than. What do we mean by the words less than? Well, for any whole numbers, A and B, A is less than B, and the symbol is written A. There's a symbol that looks kind of like an angle measurement, or maybe a triangle without the third side, something like that. It's the less than symbol. If and only if there exists a natural number k such that A plus k equals B. I'm just going to use some numbers because you know that this is what your definition is, even if you haven't ever thought of it like this before. Why is 4 less than 6? Well, because I can take the number 2 and add it to 4 and get up to 6. I have the ability to have this sort of space, this missing piece, that when I combine it with what I already have, it can equal the other value. Because this is our definition for less than. What we're going to do next is we're going to take the same idea, this idea of missing pieces of things, and we're going to do the definition but with subtraction. So the definition with subtraction is going to look almost the same. All the language at the front is going to be the same. So the language is going to say, for any whole numbers, A and B, A is less than B, written with the symbols, it looks like this, A less than B. If and only if, you know what, I'm going to shortcut this one. If and only if can be abbreviated by IFF. You ever seen that? IFF, if and only if, so we're going to abbreviate. If and only if there exists a natural number k such that. So this is the only thing that's different, is this last very tiny little bit, the equation part. Over here, it says A plus K equals B. The directions for this problem want us to rewrite this using subtraction. So what would this look like if subtraction were how this were defined instead of addition? Okay, we would subtract the K from the B, right? So A equals, I'm going to keep it in the order it was, B minus K. And I'll use my same numbers just to make sense of this, right? So before I said that 4 was less than 6. So 4 is less than 6 because 4 is equal to some number subtracted away from 6. It's the number 2. So instead of figuring out what do I need to add to the left, I figure out what do I need to subtract from the right. Okay? So that's sort of a definition from perspective of subtraction. All right, the next thing we're going to look at is 4 properties that are going to come up over and over and over again. And if you have not yet had the opportunity to take proportional and statistical reasoning, otherwise affectionately known as elementary math 2, you'll see this happen again in that class as well. Okay? Here's our first property. It's called the closure property. So the closure property says if A and B are whole numbers, then A plus B is a whole number. And the commutative property said if A and B are whole numbers, then A plus B is equal to B plus A. So we're going to talk about these before we move on. I'm going to talk about them backwards. The commutative property people don't usually have a problem with. You know that this property is true. It's what allows you to decide that when you want to add 1 plus 17, it's the same thing as adding 17 plus 1, right? It doesn't make any difference which order you add them in. This is unique to addition and to whole numbers. Just because I add 2 numbers together doesn't mean I always get the same kind of number that I had before, right? Can you think of 2 fractions that you add together and you don't really get a traditional fraction out of it? Sure, 1/4 and 3/4, right? I don't actually get a true fraction. Yes, I recognize I can write that as 4 over 4. But somehow that number is different than the numbers you started with, right? We don't have that happen with whole numbers. It's also unique because this works for addition, but it doesn't work for every operation. For example, what if you were doing subtraction? 4 minus 2 and 2 minus 4. No, it doesn't work with that. We're going to actually talk more about that later, but that's something different. All right, let's go back to closure because that's where students always get hung up. Closure property is a very unique property, all right? It feels like it's an obvious thing. You take 2 whole numbers together, you add them, and you get another whole number. Seems like an obvious thing. No big deal. That's just not always what happens, though, with all numbers. So let's take a look and think about it from a little bit different perspective. Let's say, we're going to do with whole numbers for the moment. You have whole numbers, and they're all floating around in the air in the room. You know, so the number 52 is in here, and the number 793, and the number 0, and the number 5. They're all floating around in the room. Everybody with me? And the door to the room is closed like it is now. Closure means that when I take 2 of these things out of the floating air and I add them together, their solution is still floating in the air in this room. I don't have to open the door to find it. It's closed up in the room with us already. I'm going to give you an example of one that's not closed so that you can see why I'm kind of harping on this point. Let's say that you had odd numbers. And you took 2 odd numbers out of the air. The only ones in here are odd numbers. Everything else is outside in the hallway. Only the oddballs are in the room. Right? Okay, all odd numbers. Take the number 3 and you take the number 5. And you add them together and what do you get? 8. Where is 8? It's in the hallway. So the odd numbers are not a closed set. Are you guys with me? The same thing's true when we think about it in terms of subtraction. All right? This is specific to the operation, addition, and to the set that you're working with, whole numbers. Both of those things have to have certain properties for this to work. Whole numbers and operation is addition. So let's say we kept the whole numbers. We're good with the whole numbers. They're floating around the room, but we're doing subtraction now. You take 2 numbers out of the air of the room. You take 3 and 5, and you do 3 minus 5, and you get -2, which is in the hallway. So that's sort of destroying this property by way of changing the operation. So you can destroy the property in more than one way. So that's closure, and we will come across closure again and again. So we'll have more opportunities to discuss it. Associative. The associative property says that if you have A and B in their whole numbers, then A plus B plus C equals A plus, in parentheses, B plus C. And then the identity says that there is a unique whole number 0 called the additive identity. This word additive is important here because we're not always going to have additive identities. We also will have a multiplicative one later. This is the identity property for addition, additive identity, such that for any whole number, A plus 0 equals 0 plus A, it equals A. 0 is the only number that does that, right? No other numbers do. So sometimes people will get the associative and the commutative properties switched around in their mind, which one's which. I like to think about the idea of commutative being about commuting. So like when I commute from my house to school every day, I'm switching where I am, right? I'm just switching places, and that's what commutative property does. It switches the places of the numbers. Associative does not change the order of the numbers, A, B, C, A, B, C. What it changes is who is associated together, right? So when you associate with someone, it means you're grouping yourself with them. That's what's happening here in the parentheses. They're grouped together. So the association of them changes. So what we're going to do next is we're going to take four examples, and we're going to identify which of the 4 properties each of the 4 satisfy. So go ahead and take a look and give what you believe is the correct answer next to them. You should either be writing down associative, commutative, additive identity, not just identity, additive identity, or closure. Once you have your 4, or you're stuck on one and you can't figure it out anyway, look at somebody next to you and check to see that you guys have the same things. Are they checking out? Yeah? Okay, let's make sure we all have the same things on the problems. What did you get for the first one? Commutative. What did you get for the second one? Yeah, and remember we're using the word additive with it, so if you don't have that on there, go ahead and put that in there right now. This is the additive identity. Because certainly by Monday we will have something different to talk about too with identities. What about the third one? That's commutative. Did anybody get tripped up by those parentheses? Don't think just because I have parentheses I have associative. That's not always the case, right? We want to check out that the orders of these two switched. That's what actually changed there. What's the last one? That one's the associative. So associative means that the orders remain the same. It's 532, 532, but the groupings inside the parentheses are different. Okay, we're going to do one more bit of work today, and then we're going to pause for group work. There are some basic addition and subtraction strategies, and you're aware of some of these probably. Some of them you use more frequently. Some of them sort of beckon to who you are, and some of them you're like, I would never do it that way. But it's a very good tool to know about because different kids think different ways, and you guys are going to be hit with all kinds of fun stuff when you're out there trying to teach these things to your children. So The first one is the counting on strategy for addition. So I gave the example just a moment ago of 17 plus 1 and 1 plus 17, and we can switch the order. Counting on is a very good strategy where order switching is helpful. So what you typically do is you start with the bigger number, like 17, and then you count on from there to however many more you have after that. You'll see kids using their hands a lot when they do something like this, right? So they'll do 17, 18. They put a finger up 1 because they only had to add one more and they know they're done now, right? So if you did something like 5 plus 3, they'd do 5, and then they do 6, 7, 8. There's 3 fingers up on their hands, so they know they counted on 3, and the number they ended with in their mind, 8, would be their solution. That's the counting on strategy. Sometimes it's called counting up strategy. Doubles. To be very honest, this is one that I find to be a little bit odd, but I know it was taught to my daughter when she was first learning addition, is they taught doubles. So they didn't teach all of the multiplication, or not multiplication, excuse me, the addition tables, you know, like all the ones tables, all the twos tables. The very first thing she learned how to add was 1 plus 1, and 2 plus 2, and 3 plus 3, and 4 plus 4, and 5 plus 5. She learned the doubles, okay? So why would kids want to learn the doubles, or why is this a strategy that's sort of promoted sometimes? Well, if you do know that 3 plus 3 is 6, and you're trying to add 3 plus 4, then you just know that it's 1 more than 3 plus 3, which you already memorized. That's the idea, is that 3 plus 4 is what they would call a near double. It's almost a double, and you can use your prior knowledge of doubles to then add on what you have missing. Take it or leave it. You might end up teaching it regardless, okay? So that's doubles. The next one is making 10, and to be honest, I use this one, and I'd use it with approximation, but I use this one all the time when I grocery shop to try and figure out about how much money I'm going to pay at the register. So if you have the numbers, for instance, 8 plus 6, the idea is that you would like to take the number 8 and add something to it to get to 10. And if you know that 8 plus 2 is 10, then you can know I'm going to break apart 6 into the 2 and the 4 that is the other piece of 6. So I do 8 plus 2 first, that's 10, and then I add my 4 on afterwards. Okay? You also see with this one, making 10, we'll come across this later, something called compatible numbers, where we reorganize addition in the order, like the associative property, right? So that the things that add up to 10 get added together in sort of groups of things that add to 10. So you'll hear that referenced that way as well. But the idea is to make 10s, because 10s are easier to work with than, say, 9s and 8s and things like that. A couple more. Counting back. So these are subtraction strategies now. We did addition strategies. These are the subtraction ones. And we'll do more with subtraction next time. Starting with the higher value and counting back to the lower value. So if you had something like 5 minus 3, you would do 5, 4, 3, 2, and you have the 3 up on your hand, kind of like my counting on strategy, we're counting back. You start with a higher number and you take off the number that you're subtracting away, and you see kids using their hands with this all the time. It's a very common strategy. Counting on does it the other way around. It starts with a lower number, and you count up until you get to the higher number, and you figure out how much you counted between them. So again, if I did 5 minus 3, I'd start with 3, and then I'd go 4, 5. I stopped at 5 because that was where I was supposed to stop, and the answer's on my hand. You know, it's 2. I counted up 2 more than what I was before. And there's nothing special about my hands. I mean, we can draw pictures to go along with these objects as well, right? Number lines or things like that would work really well. So these are some basic addition subtraction strategies, some of which I know you've used before and others of which you may not have. So we'll stop there today.